But I have to propose you some exercises. So for some reason it would be close to optimality. So tomorrow I will write it very easy. An exercise for you, and tomorrow I think some others. Tomorrow I'll speak about this breaking the curse of dimensionality, and the approach is based on a very simple remark. That is the following: we consider Z a random variable. Such that expectation of Z is finite, at X to be in our Q, and then expectation of Z given X equal expectation of Z, this is statement 1, and statement 2, for any beta in our Q, norm of beta equal 1, expectation of Z given X transpose beta is expectation of Z. This is statement 2. So prove that 1 is equivalent to 2. So this is an exercise for you because I have to give you exercises. Well, of course you may take expectation Z to be 0. This does not change anything. So this is the basic idea behind the breaking the curse of dimensionality approach. You see the saying that you may put here 0 if you want. Okay? Does not change anything because you can sample the variables. The variable Z, you can sample it. So the expectation of Z given X is 0 if and only if the expectation of Z given all the projections X beta is 0 forever. Okay? If you, it's very easy to understand if you project on the plane the projection of all the lines as 0.
Well, I guess X is random.
Yes. Yeah, everything is random. Well, this notation, of course, it's an abuse. It's a random variable. Strictly speaking, it's incorrect. All the statistical literature seems this way. Most of them. Yeah, it's not fixed. It's random. Okay. So let's continue. Well, and the day after tomorrow we'll try to extend this even more to Z something in N2, for instance, a random variable, a curve. We'll try to see how what becomes when X is in N2. How this could be used. This will be the idea of dimension reduction for functional data model checks. Okay. So let's continue with our story today. So we tried to use So we try to put together all the ideas in what I call the idea 1 with version A and B, 2 and idea 3. And idea 2 and 3 we briefly talked about in what I called, what is usually called the empirical process approach for non-parametric checks. I said that this is due mainly to contributions of Stutte in the statistical literature and of Gerens in the econometric literature. Now let's go back to smoothing. And let's go back to the first idea with a version 1 of A or B. And let's try to understand what people did along the years. Already about 20 years ago, Mamen and Hardel considered this quantity here. I don't have a pointer. Consider this quantity and try to, of course, they recovered the residuals inside the model, and then they tried to estimate this function here using a Nadaraya-Watson estimator. I suppose that everybody knows what a Nadaraya-Watson estimator is. Otherwise, I can write it quickly. So you regress epsilon hat on the axis using Nadaraya-Watson, and then once you get an estimate of this, you just put it in a kind of, capture everything in a kind of integral, which would be exactly an approximation of this expectation. And for the pi function, as I said, you may use something proportional to the density. I would say that I cannot remember exactly that. I would say that maybe even to the square of the density. Then, the statistics suitably centered and studentized n times h to the power q over 2 times Tn, you have to subtract the bias and you have to divide by a suitable standard deviation. Then you will get a standard normal under the null hypothesis of a correct model, which means the expectation of epsilon given x is 0 on a show. So this was the idea of Hardel and Mamen. And what is a pity in some sense is that with this idea, which is very natural, because you take the square of the function that you'd like to show that is 0, you multiply by a positive weight function, you take the expectation, and you check if this number is close to 0 or not, or the estimate of this number is close to 0 or not. So it's a very natural idea. Unfortunately, this type of statistic will induce a bias term, and this bias term, of course, is unknown, has to be estimated, and this makes this approach a little bit less convenient than what we will see in a second. That is a similar approach, but based on idea 1b, not on idea 1a, as one does with this quantity here. Another approach was considered by Holger Depp and also by Fan and co-authors. Both are papers in analysis statistics. They looked at the variance. They looked at the variance of the residuals under the null and under the alternative, and they compared the variances. And if the variances are sufficiently close, then you may say that you're under the null. The model is correct. Let's say how all this can be written in the case with one regressor, as Dete considered. So he considered the difference between the estimate of the variance under H naught minus the estimate of the variance under H1, H alternative. This is more restrictive, so here the residual should be more variable than under the alternative. So UN is expected to be positive. So the estimate of the variance under the null is exactly the one you obtain with the residuals obtained inside the model. where theta hat is an estimate of the parameter, for instance by least squares. And the estimator under the alternative, then the residuals are obtained by non-parametric smoothing. You project your y's on the axis, you take the difference, and you build an estimate of the variance with this residuals. You make the difference of the two, and then UN, suitably centered and studentized, will behave like standard norm. Let me point out that in those cases, the test statistics, the rejection region is one-sided, because either the quantity is positive, or the quantity will either the quantity is zero, or the quantity will explode to plus infinity. Just think a little bit about what is here. This is either zero or positive. So Tn would estimate something positive under the alternative. With this inflating factor here, this will go explode to infinity. The same happens here. If you are under the alternative, this difference will be strictly positive. With the inflating factor, this will go to infinity. So all these statistics that centrally, suitably centered and studentized have a normal distribution under the null. Under the alternative will explode to infinity. So the test, the rejection region for all this test is one-sided. So you just take your statistics. For instance, if you want a test at level 5%, you just compare with 1.645, and if it's larger, you reject. The model is not correct. If it's smaller, you do not reject. You say we have no evidence to say that the model is not correct. Okay. Well, some alternative routes were proposed by Kitamura and co-author. I will come back later on that. Now you understood that I presented all the ideas, but the one that I will get into the details, the 1B. So let's go to tell a little bit more in more detail how it works with 1B. So recall that 1B was something like condition expectation is 0 if and only if this marginal expectation is 0 with W a weight function. This function is unknown, this product between this expectation and W, and we have to estimate it non-parametrically. So, as I said several times, W will be proportional to the density. And let's try to see how this could be done, how this could be estimated. It's quite simple to understand if we remember this. As I said, this expectation here we will approximate it by taking the empirical sum. So it will be 1 over n, the sum over all the samples, epsilon I, and here we'll have something like with phi x is expectation epsilon but it's very easy. If we had this function phi, it would be very easy to build an approximation of the left-hand side quantity here. Of course, we do not have it, but this is the idea to use, to try to estimate this function and to put it together in a sum. This is exactly what is written here, except that for estimating, well, I call this pi. Sorry, I call this pi. Let's call it pi. So here is a pi, and I call it minus I and h. Why minus I? Minus I because we'll take a leave one out version. We'll see in a minute what does it mean. And it will depend, of course, of the degree we will smooth to to estimate this non-parametrically, and this is given by the bandwidth h. And this statistic, we will inflate it by n h to the power q over 2. And this will be the object to be studied and to understand its behavior under the null and under the alternative. Why leave one out? Well, it's not absurd to think that this is a function that you estimated that you want to apply for the observation xi. So you estimate this function using all the other observations, and then you apply it to the new observation xi in some sense. And this is exactly the idea of a leave one out estimate. Okay? So the leave one out estimate will be exactly the one you see here. Okay? It's exactly the numerator of the Nader-Iwalson estimator, because don't forget, here you have a ratio usually, and the denominator you have the density, but since you multiply everything by the density, you only take the numerator in the Nader-Iwalson estimator, where you regress epsilon with respect to x, and this is the pi hat function. And when we put this pi function in the Tn statistic, what you obtain, well, sorry, some notation, kh is kx over h, where k is a q-dimensional smoothing kernel and h is the bandwidth. Okay. Please ask questions.
We're trying to understand. Okay, actually the bandwidth. Okay.
Yes.
I have a question because T capital depends on h.
Yes.
So we have a random process which depends on h.
Yes.
So my question is how, in this case, Tk of h may be in some sense strongly dependent, and I guess that the distribution is quite similar to the distribution of the Brownian motion, say with respect to h. This is a random process, so which behaves like a Brownian motion, I think. And so my question is how we can take a decision in this case. Well, because it's not, we have a family of, in fact we have a family of tests which depends on h. Okay, and so we have a typical multi-testing problem here, and my question is how we can take a decision in this case.
Well, this is, in fact, what we will do is we will let h to decrease to 0, because the idea would be to get a consistent estimate of this quantity. And then when you let h to decrease to 0, what you obtain would be a centered Gaussian law for h going to 0.
So this will be misleading discussion. So theory probably means that what happens if you consider many different h simultaneously?
Yes, of course, because you do know, h is unknown. There is no argument for choosing h.
Here
it may be small or large, we do not know. It depends on the underlying function. If the underlying function is smooth, then h is large. If it is not smooth, it's small, and so on. And
when you say that it is unknown, you believe anyway that you let it go to 0, I suppose.
Yes, that's right, but we do not know how small it is.
Okay, so the rate to which depends to 0 is exact. One should be able to select this rate in order to detect in the best way alternatives. And the regularity of the alternative, you do not know it. This is what you found. But some answers were given by your colleague in a paper with Horowitz, where he considered, but this is a bit later he considered a grid of h's and took the maximum of the statistics over this grid, which decreases to 0. And then you get a law that is, of course, no longer a pivotal law that you have to determine by resampling. And this is a way, one possible way. The work was developed further in another paper 4 years later by Gerard Laverne, who did a similar idea, but using a studentized, another type of penalty, to choose age in a grid that decreases, an exponential grid not that
Why
decreases.
I do not understand why we need a grid, because TH are strongly dependent if you use kernel estimators, so it's not clear why we need a grid.
No, we don't need, but it's the same. So you can take. It will be the same. If the grid is dense, so it's a matter of how much you pay. It's technical issue. You can take the continuous. But so this is the step after, so I think so. Maybe Valentin will comment on this later. But at the moment, I suppose H is
H is deterministic, is goes
just
to,
one for fixed n is one H.
yes, for H is will be a sequence of values that goes to 0, deterministic, and we will not at this level. For the moment, we will not look at how H should be selected on a grid or on an interval, whatever. We will only ask H to go to 0. If it's some interest to tomorrow, because I could remember the principal facts in the paper of Volodya wrote or Gerla wrote, I can show you how what was the suggestions they put. The idea being to be able to detect, to be optimal, to detect the alternatives, to be adaptive to the regularity of the alternatives. So at this level, the H is a bandwidth that we will decrease to zero with a sample size. So, the idea of using a leave one out version is to make this statistic to be unbiased or almost unbiased. Imagine that instead of taking when we take a leave one out version of the pi, of this estimate of pi, and we inject we plug in the definition of Tn, what we come up with is a double sum over A and G for indices A and G, I and G that are different. This is a so-called U statistic. If you take all pairs of indices I and J, you get what is the so-called a V statistic. And this U statistic, if you take, let's say that you take the sum of epsilon I, epsilon J, I different J, of 1 over HK, sorry, HQ, K xi minus xj over H. You take expectation of this. This will be 0 if epsilon if the expectation of epsilon given xi is 0. So with the true epsilons, this statistic is centered. There is no bias. Please remember that this statistic under the null hypothesis should estimate 0.
You should give it as an exercise to check.
Okay, please check that this is 0. Okay?
Expected value of this is 0.
And the expected value is 0.
Very difficult to see.
And find also the expectation of 1 over n, of sum ij1n, epsilon I, epsilon j, k xi minus xj over h. If 1 over h, q, k. So find the expectation of this and check that this is 0, and you will see the difference between the two. And you will see that the second expectation is strictly positive. That is, there is a bias. And this expectation, you will find it to depend on unknown quantities. So you have a bias statistic. The bias depends on unknown quantities. And what you want to estimate under the null is 0. So it's reasonable to think that perhaps it is much easier to work with the unbiased statistic. You don't have to remove the bias. You no longer have to remove the bias. Okay? That is another reason why we use this leave one out version. Because at least with the theoretical epsilons, this statistic should be unbiased. The bias, these statistics will really have, because we don't have the theoretical ones, will only be given by the error ones is obliged to have because you do not observe the epsilons. But these errors will be the errors given by the parametric model. And usually will be less important than the whole contribution of this statistic. So that is why asymptotically at least, this statistic will behave almost as this one. This is the idea behind all the tests, the test that is put in place. Okay?
Would it be true to say that until this slide everything could be done for non-ID case, and this is where it breaks down in the theory, or it was before somewhere? Like
What do you mean by everything?
Dependence in excess epsilons. Because like what you said before, you could do for dependent data, I guess, everything.
So, this could certainly be done for dependent data.
Yeah.
Yeah.
So the first time it breaks is here when the expectation is.
It breaks, but not definitely. It could be. You may have some dependence. There are some versions where you introduce some dependence, but it becomes much more complicated. Here, to get convergence to a stochastic process with dependencies, the price would not be very high. I mean, it will in the contributions after the initial papers, people took some dependence of most of the users. But with the quadratic form, with the smoothing approach, the price is a bit higher. It becomes more complicated. That's true. So, suitably studentized, so no centering needed. We just talked about the bias. On the H naught, the statistics Tn has standard normal limit. One-sided test, of course. Oh, sorry. To estimate the variance of the Tn, to studentize the statistic, we have to estimate the variance. And in fact, because Vladimir asks me to give exercises, please exercise. Another exercise. Let Tn be 1 over n minus a, 1 h cubed, I before j, epsilon I, epsilon j, khig, where khig is kxi minus xj over h. Show that the expectation of Tn given x1, xn is 2 over n minus 1, h to the power q, sum a before j, sigma squared xi, sigma squared xj, k squared hig, where sigma squared x is expectation of epsilon squared.
From variance, not
Oh, sorry, variance. Of course. Well, the expectation of the square is the same. Tn is, and of course, epsilon i's, xi's is 0 for all I. Okay? So you take this statistic and you compute the condition of variance given the x's. You look like the k's are constant, and then you find this. It's just take the square of this, and then you will have a sum on 4 indices, A, J, K, L, A different J, K different L, and then you take expectation, conditional expectation, given the axis. So you will have products, epsilon I, epsilon J, epsilon K, epsilon L. And then you should remember the independence. You'll see that these products will always be 0, except if K equal I, J equal L, or vice versa. From there comes the 2, from the vice versa. So then you obtain exactly what is written. Okay?
You just solved the task.
It was a hint. It was a hint, yeah. This is, okay. Now, of course, this sigma, in general, this sigma is unknown because we do not want to impose conditions on epsilon. We already tried to estimate this non-parametrically. Of course, the expectation of the square of epsilon given x should also, in general, should also be estimated non-parametrically. Fortunately, if you consider the statistics with the squares here, without hats, you take the statistics with the squares, and you take again the conditional expectation, you obtain the same quantity here. Is it clear or not? So another exercise. Now this is a remark, it's too simple. If you take the statistic expectation of sum y different j, epsilon square, epsilon j square, k square, hij, given x1, xn. Okay. This will give you the sum y different j, sigma square xi, sigma square xj, kij, kh, ig to the square. Okay. For the same reasons, you just use independence of the epsilon I and epsilon g. So perhaps it's with the epsilons here, we get an easy estimator of this quantity. This is apparently a good idea. Of course, you don't have an epsilon, so you have to put the hats. So here are two estimates. Here are two estimates of variance or conditional variance of the quadratic form that was on the previous slide. This one is based on a non-parametric estimator of the variance function. This one is simply based on the residuals to the square. So, at this stage, we can believe that this is similar. Okay, I don't know if I have to say it at this stage or, maybe we can say it here already. Let's make another remark. What happens? Let's make another remark. H null is not true. And that Y is, let's say that we are in a regression context, nonlinear regression. X theta naught plus some function of x plus some epsilon. And the expectation of epsilon given x is 0. When you take the sigma x is a conditional variance of epsilon given x, which is exactly the same as the conditional variance of y given x. Because the function of x is constant in the conditional. But when you take epsilon squared, this is, sorry, when you take y minus mx theta naught, and this is a quantity that you can build from your sample. This is what you can build from your sample, because you only observe y and delta. You do not know that you only observe y and x. You don't know this function. So this will be epsilon plus delta x. Okay? So, the exercise would be then compare the two estimates of the variance of the quadratic form. Which one seems preferable for power? Of the test. Since Volodya told me that I have to give you exercises, I cannot stop giving you exercises. The idea would be to understand by simply calculus that this is a very bad idea for the alternative, and this is bad because it will not change. The sigma function does not change if you're under the alternative or under the null. So this estimator will be the same under the null, under the alternative. And when you try to estimate the sigma function, you'll produce the same result. While if you use this idea, you will inflate the estimator due to the fact that the difference between the residual that you can compute in the model, will be the epsilon, which has this conditional expectation plus the deviation from the null. So you will inflate, in fact, the estimator under the alternative if you use only the square of your residuals. And if you'll see in a minute that what we will do with these two quantities, we'll studentize the Tn by one of these two quantities. What means, if you're under the null, there will be no difference in theory. But if you're under the alternative, you will divide by something that is larger. You overestimate conditional expectation of the statistic given x. Overestimating means that you render your test statistics smaller. That means your test will be harder for the test to detect the alternative because you divide by something larger than is necessary. This is the sense of the question I put here. Okay? So the result I already announced is the following. Under some technical conditions that could be found in the papers that I put in on the references, if H0 holds true, the ratio Tn over Vn converges in law to a standard normal distribution. So the test that you can put in place is the following. Reject H0 when T divided by Vn is larger than the quantile of the normal statistic, the quantile of order 1 minus 1. As I said, for instance, with 95 alpha equal to 0.005, here is 1.6465. This was proved for the first time in some work in econometrica by Fan and Lee and Zhang in Journal of Econometrics. What is behind this theory? Behind this theory is a central limit theorem for degenerate U statistics. What I call degenerate U statistics is an object like in the brackets. This is a degenerate U statistic. I may say in a second why we call it degenerate. So central limit theorem for degenerate U statistics. You have epsilon I xi I decalculus of epsilon x, and you suppose that epsilon is of zero conditional expectation, that sigma squared x to be the conditional variance of epsilon. And suppose the sigma square is bounded away from 0 and infinity, and define this statistic, define this to be the variance estimator, and then it could be shown that if the density, under some conditions, the density of x is bounded, k is symmetric bounded density, and the bandwidth satisfies conditions like this, then T0n over Vn converging law to a standard normal distribution. The first result of this kind was proved by Peter Roll in Journal of Multivariate Analysis in '84. Probability and related fields, de Jong proved much stronger versions that in particular are conditional versions, conditional on the x's. He put here some constants, and he proved five versions of this central limit theorem. And Guérin and Lavenia refine a little bit more. They give a variation bound for the convergence of this statistic to normality. So perhaps that other results are present. In particular, some dependence was allowed in other results for this central limit theorem here. Some dependence was allowed and some results exist. But already, if you have a conditional version given the axis, you may introduce some dependence through the axis and just suppose that the epsilons are independent conditionally on the axis. And in some modelings, this is enough to introduce dependence through the observations. In some, yes, because he's doing some, he's using some constants here, constants. And if you check the conditions for the constants, it's like checking the conditions. These are his constants. The Jean could be seen as a conditional version. So this is the main tool that is used behind this approach. This is a main tool, and this main tool allows to state this theorem that I put it previously. And the convergence in law could be, as I said, given conditionally on the axis. In the preliminary versions in '96, the theorem was based on Peter Roll central limit theorem. It was not a conditional version. Okay, so this is the main tool for proving asymptotic normality. What about the for proving that the test behaves in the same way? Then all what it remains to prove is that, at least from asymptotic point of view, The difference between the statistics that uses epsilon estimated and the statistics that uses the true epsilons, that are theoretical, you don't have them, is negligible asymptotically, and the ratio between the variance estimate and the true variance that is written here is also negligible in the sense that the ratio goes to, oh no, here is not correct, sorry. It's 1 plus OP1. I'm sorry. 1 plus OP1. Just to check if you're still awake. Okay. Well, the critical, if you start looking about how this works, you try to generate random variables, whatever epsilons, uniforms, whatever normals, whatever you have in mind, and you construct these quadratic forms, and you try to check if the central limit theorem, the normal approximation is accurate for small samples. You will notice that in general it is not really the case, at least up to 50 observations. So even to an exercise, if you have interest to simulate some epsilons and to do this quadratic form with some x's, you may see that the shape of the distribution is not always very close to normal. In particular, there is a skewness that is too high, much too high for small samples. But then, this is one point. The second point, please do not forget, we'll try to understand the effect of theta, maybe tomorrow, writing the decomposition of the statistic. Please do not forget that for the moment, we said that maybe under suitable conditions, the difference between the theoretical statistic with the true epsilons, and the one that you use in practice with the estimated epsilons, this is negligible. This is true in theory, but in practice, of course, it may matter, and this may make your convergence to normality even slower. So, it is not absurd to think about some resampling techniques in order to approximate your asymptotic distribution by some bootstrap distribution or resampling distribution. And how this may work?
Sorry, just
yes.
You said slower. So is it like the rate is slower?
No.
Just worse.
In the higher orders. No, not okay. The rate will not change, but in the higher orders. So, the bootstrap could be generated, could be used as follows. As usually, when you work with regression type models, and here we are in this context, regression type models, it is reasonable to keep the axis and to generate new y's using the model. This is a way you will keep the model structure, and your bootstrap is expected to provide accurate approximations of your critical values. So another idea would be to select the couples y and x, but this will not preserve your model structure and is not recommended. And some work in the 90s proved that this is not a recommendable bootstrap procedure. The one to do is to use a model, try to keep the axis and produce new y's through the model. Let's see how this could be done in the case of regression models. You may estimate the residuals inside the model, very simply. And then you have to, since you keep your mean, you have to generate new errors. And one way to do it is to perturb your epsilons had by some distribution that is of zero mean and the second and the third order moments equal to 1. The second order moment equal to 1 is quite easy to understand why, because you do not want to break the variance structure in your residuals. The third order third order moment equal to 1. This is a little bit more difficult to understand. Was proved by Enomaman when in his paper in '93 that this provides more accurate bootstrap. So with this condition, there is only one distribution. If you consider 2 points distribution, the simplest one, and is given by what you see here. By the way, in the paper of Mamen, there is another distribution built from the Gaussian distribution for somebody who does not want to use a discrete one, but to use a Gaussian one. He proposes a distribution satisfying these 3 conditions, and the proposal is wrong. The proposal is wrong. It's not true. The distribution he proposes in the paper does not satisfy. There is a mistake in the constant. We notice this when we try to compute. Okay, so exercise for tomorrow. Please find the mistake in Mamet's paper. So it will be very easy. It will be very easy to understand because there is only one proposal with a Gaussian, and you will see that this proposal is not correct. Okay. So then you generate, using this bootstrap perturbation, you generate these new y's, and then you have new samples, and with these new samples you do exactly what you did with your original samples, exactly what you did. And then you generate new statistics, and you compute as many as you want, and you obtain the so-called bootstrap problems. Well, here is another version, I will skip it. And here is what I wanted to say about detection of the alternatives. This was a question of Yuri about how the test will be able to detect alternatives. Maybe we can get, it was not my plan to get into the details, but maybe tomorrow we can get. I have something like 100 slides, but maybe I can stop more tomorrow and talk about this. Let me show you what I was supposed to present today. Anyway, I cannot change it now. So, all the tests presented here detect alternatives that are fixed. That is, the probability that the conditional expectation is in the model, the conditional expectation equals a function in the model is strictly smaller, bounded away from 1. So all the tests will be able to detect such alternatives. And under suitable conditions, then the test could also detect alternatives that are approaching 0, things like this, where you have a regression function from the model and you add some perturbation with a sequence Rn, and the function fixed for the moment, let's say, delta, and Rn is going to 0, delta is not known. So, Gerens-Studer tests, that is the ideas 2 and 3, will be able to detect such alternative as soon as square root times Rn goes to infinity. Rn is decreasing to 0, but slower than 1 over square root n. While kernel-based tests will be able to detect such alternatives as soon as square root times h to the power q over 4 times Rn goes to infinity. So Rn should decrease to 0, but slower than 1 over this. We'll try to understand more. We can make some calculus to see exactly, but perhaps it's better to have this all the board.
So local alternatives like root and alternatives excluded from both cases, right? Even for a student.
Root and alternatives, what you usually call root and alternatives, R is something like C over square root n.
Yeah.
And you let C grow, and then you detect it. With probability going to 1. Because this is, if you let C to grow to infinity, then the probability to detect goes to 1. As slowly as you want. If you keep fixed C, or you take C over square root n, then the probability to detect is lower than 1. Will not go to 1.
Like the usual Kolmogorov-Smirnov test can detect without C taken to infinity. Just constant over root n, constant fixed.
But I'm not sure that the probability to reject is 1, is going to 1, if C is not going to infinity. I'm not sure. It's large, but it's not 1. If you want to be 1, you have to grow C. You can be arbitrarily close to 1 if you increase C, but you'll never be 1. I think it works in this way.
It means that the kernel-based are not so good as because Rn we want to detect with the smallest Rn, okay?
Yes.
And if you look at the two formulas, we see that the Rn, in the first case, we have root 1 over square root n.
Yes.
And in the second case, we have a larger rate.
For instance,
that means that the kernel base are not good.
This is the main criticism people doing empirical process approach tell you when you submit a paper with kernel smoothing. But
that's really true.
But what Volodya showed is with this idea of maximizing with respect to H, even on a grid, if you are under such type of alternatives, what you will select will be an H that is something like 1 over square root of log n. Or 1 over log n.
Yeah, basically the Beerens test so requires some condition on the function delta. This means it provides root n sensitivity, but in some directions. Where it's not typical directions actually. And if you want to be sensitive in all directions, then this is what kernel-based test will do. So this is another interplay. So
I think in the first case, delta should be very smooth function or something like that. Because
no, it's delta should be orthogonal to the parametric family. And it's very difficult to combine two conditions. So at least it should have a significant component orthogonal to all functions from the parametric family. And this automatically produces a very little function which has not so much energy. So basically it's a long discussion. Who are interested in it could probably check my paper with Joel Horowitz. We will make exactly this discussion to address the point why you should actually apply kernel-based tests, not this Kolmogorov-Smirnov type tests which are not sensitive at all. So formally you think it is root n sensitive, therefore it is sensitive, but it has no power at all. This is very well-known fact.
In fact, in another paper in econometric theory, Guérin and Laverne proved that from the minimax point of view, the Beerens test has trivial power.
Yes, exactly, because it's not uniform with respect to delta function.
So this is only an argument for this type of alternatives. It seems to be better. But please remember that H only has to go to 0. So you may take as slow as you want. So for this type, if you really believe in this type of alternatives, you can all get as arbitrary as you wish to the power of the Beerens, by taking an H that is very slow. This would not be a problem. The problem would be to be able to detect it from data. And this is exactly what Spokojny and Horowitz did with their adaptive procedure. And they showed that their adaptive procedure, when you are not on the such alternatives, you detect them up to some log type factor, while the variants do not. Not at all. Could have trivial behavior. And when you are under this type of alternatives, even if you don't know, the same selection procedure of H brings you a H that goes very slowly to 0, or order log. So you get almost the same power as the variance against such type of alternatives. So for somebody that wants to read carefully the paper of Spokojny and Horowitz, would understand immediately that variance, all the empirical process tests are in reality worse than the smoothing-based tests.
There is additional critique to the smooth-based test, saying that it depends on the way how you choose window and.
But this is the discussion we are talking about. Yeah, this is what we are talking about. How to choose the bandwidth. And okay, because it's such big issue, I will try tomorrow to present the basic facts from the paper of Volodya. And then you will see that by something that is data-driven, you just look at your data, you apply the procedure, you adapt to any situation. Think that variance cannot do it. This is an automatic selection. So this is what I was written here, detection of smooth alternatives. And then I did not put too much, I just put some elements that are, tomorrow I can detail a little bit if all this created so passionate discussions in order to make this more clear. So when delta belongs to a class of functions, the deviations are not uniform, and the result is uniformly with respect to this class of functions. Okay, so let's try to finish our discussion with some comparisons to try to understand the pros and the cons for these two. So starting from different characterization of the conditional moment, two types of approaches were presented, empirical-based and kernel-based. So kernel-based and empirical-based are omnibus in the sense that they detect any fixed alternative, both of the type of tests. The critical values for empirical process tests have to be computed numerically. Bootstrap is necessary in any case. The kernel tests work with critical values given by the standard normal law, but of course, finite sample corrections, small sample corrections are also required. We have to be honest, with small sample is not, the quadratic form is not standard normal under the norm.
Can I answer that?
Yes, yes please.
So these omnibus tests, I mean empirical process tests, they are omnibus. So, but at the same time you say that there are some alternatives, local alternatives, where they have trivial power.
Yes.
So if like these deltas, delta x, so if you take like this as a fixed alternative, would it be also consistent against that delta x which is not consistent in local framework?
I'm not sure. Fixed alternative, you only have one delta. You don't move it.
Yeah, but
where the empirical processes test will be trivial is when delta moves with the sample size.
okay.
Imagine a sine function where you change the frequency with the sample size. This kind of alternatives, the variance test could completely miss it, while the kernel-based ones will be able to detect if the row n is not too fast to
But
0.
if delta x doesn't change with n, then they are
All of them are detecting. All of them.
detected.
For a fixed alternative, fixed is far away from and it does not move, then all the tests are consistent. No problem.
No, local, but with fixed delta. Delta x is fixed, and then the rate.
Oh, okay. So okay, now I get it. What you mean is
Yeah, this
this
Yeah.
variance empirical bays are detecting this
Okay.
under the condition you see here.
Okay.
It's not a problem.
But if delta is a problem,
Huh?
if delta is not in the parametric framework,
Of course, yes. When I write this, is in fact the condition would be the expectation between delta and the gradient of this with respect to theta is 0, which means that this is orthogonal on the model. Delta should not be in the model, because if delta is in the model, all this is a function from the model. Could be a function in the model. So what is still needed is a condition that tells you that delta is a real departure from the model. And this condition is usually written by saying that expectation between delta times the gradient of this with respect to theta is 0. Because in this way you are sure that you are not one piece of the model. Okay? It's a... So just to finish, because it's time to finish, I think. So power, Pitman alternatives, what I call Pitman alternatives is with fixed delta. Rn, but with fixed delta. This is, so this is to recap everything. So it detects that approaches, Pitman alternatives that approach slower than 1 over square root n, while the kernel there is a loss here. In practice, Rn is not given, and the choice of the optimal bandwidth is not obvious. Well, the smooth alternatives is what we discussed already. And I think I will stop here, because then I can talk tomorrow in more detail about how to choose the empirical, the smoothing parameter. So we'll stop here. It's 7:30.
okay, let's thank the class, and any questions for this part of the presentation, except what is already asked? So many questions done. So then we restart at the same place at the same time tomorrow, and please do the exercise.